Hello, welcome to Learning Box. Today's discussing topic is entropy and information gain in machine learning. Analyzing entropy, the role of information gain in decision trees. What is entropy? Entropy is a measure of the system's tendency to move from order to disorder, with increasing entropy indicating a progression toward greater chaos or dispersal. Let's discuss more. Entropy is a term that comes from physics and means a measure of disorder. More specifically, we can define it as: entropy is a scientific concept as well as a measurable physical property that is most commonly associated with a state of disorder, randomness, or uncertainty. The term and the concept are used in diverse fields, from classical thermodynamics, where it was first recognized, to the microscopic description of nature in statistical physics, and to the principles of information theory. In information theory, the entropy of a random variable is the average level of information, surprise, or uncertainty inherent to the variable's possible outcomes. In information theory, entropy is a measure of the uncertainty or unpredictability in a set of data or a signal. This concept was introduced by Claude Shannon in his groundbreaking work on information theory. Shannon's entropy quantifies the amount of information or uncertainty inherent in a probability distribution. It's often used to understand the amount of information needed to represent or encode a message. Information gain is a key concept in information theory and machine learning, particularly in decision trees and other algorithms used for classification and regression. It measures the reduction in entropy or uncertainty achieved by partitioning a dataset based on a certain attribute or feature. Essentially, information gain helps determine which features are most useful in splitting the data to make predictions or classifications. Information gain is the difference in entropy between the initial state and the final state of a dataset. It provides valuable information about the data structure. Common splitting criteria in decision trees. Information gain, gain ratio, Gini index, chi-squared test, and variance reduction. Information gain. This criterion, based on information theory, measures the reduction in entropy resulting from a split. A split that reduces entropy more is considered better. It is commonly used in algorithms like ID3, C4.5, and C5.0. Gain ratio. A modification of information gain, gain ratio addresses the issue of this toward attributes with many values. It divides information gain by the split information, which measures how broadly the data is split by an attribute. Gini index. The Gini index measures impurity in a dataset, with a lower Gini index indicating less impurity or greater homogeneity. It's used in the popular CART, classification and regression trees, algorithm and works well for binary splits. Chi-squared test. This statistical test can be used as a splitting criterion, especially in algorithms like CHAID. It assesses whether an observed distribution is significantly different from the expected distribution. Variance reduction. This criterion is used primarily in regression trees. It measures how much the variance is reduced by splitting the data. A split that results in greater variance reduction is favored. Splitting criteria are rules or methods used to decide how to partition data at each node in a decision tree, a common structure in machine learning for classification and regression tasks. The choice of a good splitting criterion is crucial for building effective decision trees because it affects the accuracy and interpretability of the resulting model. Fine-tuning decision trees involves adjusting various parameters and strategies to improve their performance, reduce overfitting, and enhance generalization. This process is crucial for achieving accurate and robust models, especially when dealing with complex data or building large systems. Pruning techniques are cost complexity pruning and reduced error pruning. Cost complexity pruning. This approach prunes branches based on a cost complexity parameter, balancing model accuracy and complexity. It helps avoid overfitting by removing less informative branches. Reduced error pruning. Prunes branches that do not improve accuracy on a validation set, leading to simpler and more robust trees. A decision tree is a tree-like structure used for decision-making, classification, and regression in machine learning. The components of a decision tree are root node, internal nodes, leaf nodes, and branches. The structure and flow of a decision tree are decision tests, splitting criteria, recursive structure, classification and regression, and path traversal. Overall, the structure of a decision tree provides a clear and intuitive approach to decision-making. Entropy in decision trees. Entropy is commonly used in decision trees to evaluate the quality of a split. It helps identify the attribute that best separates the data into different classes or groups. Entropy for decision trees. Given a dataset with multiple classes, the entropy for the dataset is calculated by considering the proportion of each class and then applying the entropy formula. The entropy for a dataset is equal to minus summation of the probability of outcome x multiplied with logarithm base 2 of the probability of outcomes. Entropy of a split. To calculate the entropy of a split, consider the subsets created by the split and calculate their entropy. Then, the total entropy for the split is the weighted average of the entropies of these subsets. Maximizing information gain. To maximize information gain, we need to select the feature that leads to the largest reduction in entropy. This ensures better decision-making in the tree. Challenges and limitations. While decision trees are powerful, they can be prone to overfitting and may not handle continuous attributes well. It's important to address these limitations. Future research and trends. Advancements in decision tree algorithms, such as random forests and gradient boosting, continue to drive research in the field of machine learning. Entropy and information storage. Entropy impacts how information is stored and transmitted in various systems. Data storage. The entropy of a dataset determines the minimum number of bits required for storage. Efficient data storage relies on encoding schemes that minimize redundancy and compress data with high entropy. Transmission and communication. Entropy affects the bandwidth required for data transmission. High-entropy data needs more bandwidth, while low-entropy data can be transmitted more efficiently. Redundancy and error correction. While entropy-based compression reduces redundancy, some level of redundancy is necessary for error correction and detection in communication systems. Techniques like Reed-Solomon codes and convolutional codes introduce controlled redundancy to ensure data integrity. Machine learning. Entropy is used in decision trees to measure the uncertainty in data, guiding the tree-building process to achieve optimal splits. Decision trees and information gain are widely used in fields such as finance, medicine, and marketing for predictive modeling and decision support. In conclusion, understanding entropy and information gain is crucial for effective decision tree modeling. It plays a pivotal role in feature selection and classification. Thank you for watching. We appreciate you taking the time to watch our video. If you enjoyed it, don't forget to hit the like button and subscribe to our channel for more content like this.